Thank you everyone and good afternoon. Last session at ACI, so this virtual ACI, so I'm hoping that whoever has made it to this point are really resilient and are really excited. So very, very nice to see all of you. I'm going to talk about some of the work that we have recently done with UHPCs. And it's based on the funding that we have from Arizona Department of Transportation. My co-authors or co-researchers in this work are Professor Barsimo Basher, who is a professor at ASU, and Dr. Ashir Shora, who is a postdoctoral researcher. So again, I'll do some customary introductions of UHPC just to get into the topic. Um, Conventional concretes of about 25 to 50 megapascal compressive strength. We talked about high performance concrete quite a bit with silica fumes at vent and lots of high performance bridge decks, and that's what's about 50 to 100 megapascal. And now we're talking about 150 megapascal plus strength of 25,000 psi strength or more for UHPCs. Tensile strength also is high, about 10-15 megapascal. You need quite a bit of steel fibers to get the ductility and to get the crack control that you need for such highly durable materials. Fundamentally, we rely on a very low water to binder ratio and optimal particle packing that enhances the strength and durability. So, from a fundamental viewpoint, UHPC is everything that you teach a fundamental undergraduate concrete materials class on how to make good concrete. You make that good one even better or add a few more bells and whistles to it to really do a lot of things that conventional concrete cannot do. So our focus was on bridge element connections for accelerated bridge connections. You can have UHPC bridge decks, you can have UHPC overlays, you can have UHPC column encasings, a lot of different things. And our work was both material design and development and large-scale structural testing, as well as development of procedures for structural analysis. And I'm going to present only a small portion of that work today, focusing on the rheological parts. So field connections, if you have to have deck level connection between precast deck panels and field casting, you need small simple connections that doesn't require post-tensioning or large volumes of field cast concrete. Therefore, applications like this where you can have a really flowable mix flow between the panels and connect them and give extremely high strength and durability is a very helpful thing for bridge engineers. The challenges with material design for UHPC, again, things that have been told over and over again in pretty much every UHPC literature that you can see. Commercial mixtures are quite expensive. You need to have low water binder ratios to obtain strengths of greater than 150 megapascal, which requires a lot of admixtures, which adds obviously to the cost and other issues with compatibility between multiple admixtures. If you're using a water reducer, a set enhancer, a viscosity modifier, etc. They need to be self-compacting for bridge deck connections. You're looking at small volumes and you're looking at closely packed areas that it has to flow into. You need extremely fine powders to ensure particle packing and reactivity. That will again influence the water binder ratio, admixture contents, etc. And we also talk about small aggregate sizes and high binder content. Typically, UHPCs deal with most of the commercial UHPCs, and most of those what are used are mortars, basically cement sand mixtures with a bunch of other particles. But we also now develop small aggregates into UHPCs to ensure volumetric stability and also to control the cost a little bit. So here are some common UHPC mixtures that are available in the literature, and you can see that very high cement content, 700, 800 kilograms per meter cube, and a bunch of other things in sand. And you can see silica fume, ground quartz, steel fibers in some cases, all of that. So, and obviously, if you're looking at very high amounts of steel fibers and very high amount of admixtures, the cost of your concrete is going to go up. So it's not surprising that typical UHPC mixtures have been costing 10, 15 times that of conventional concrete mixes. And that is expected with all the extra materials that you need expensive materials that you need, plus the fact that most UHPC mixtures are commercial mixtures, are proprietary mixes, and so there is a little bit of added cost because of that. So our approach was to develop a rational material design procedure that satisfies pretty much every requirement that you want, to go away from using a certain set of materials that we have and then putting them in and creating a UHPC mix. We went back and said, okay, what do we need to select? How do we select the binders and admixtures and water binder ratio? And what parameters would you need? So you need actually, effectively, you need three different things from the paste component. We'll come back to the aggregate part later. But if you talk about the paste, you need to have optimal packing of particles in the paste. You need to have enough reactive materials in the paste, and you need to have it self-compacted. You need to have it flow quite well. That is from the paste point of view. When you come to aggregates, you need aggregate sizes and amounts that are conducive to the rheology that you need, and of course with the strength and other properties that you need. So what we looked at was a combination of a first level binder design or a paste design and added on an aggregate design, both based on fundamental scientific principles, completely doing away with trial and error proportion. Okay, so particle types, if you look at it, you have the range of particles all the way from nanosilica, which is a few nanometers, all the way to coarse aggregates, which are a few millimeters. So you have about 6 orders of magnitude of sizes within the materials that you are using. And the shaded area that I'm showing here, so the shaded area that I'm showing here is pretty much all the materials that we have used, right from silica fume all the way to some size of coarse aggregate, not the entire coarse aggregate size, but some size of coarse aggregate until about, I think, 6.5 millimeters or so. So here are the particles. We used ordinary Portland cement, we've used slag, we've used fly ash, metakaolin, limestone of different particle sizes. Not all of them in the same mix, and I'll explain that as we go through, but combinations of these different materials based on certain criteria. Slag and metakaolin are helpful, and fly ash also are helpful to pack the particles as well as to give you additional reactivity. Limestone helps with dense packing of the microstructure, and if you have enough amount of aluminates in the system, for example, like slag or metakaolin, you can have carbonate synergy with that, and you can form carboaluminates, which also will give you more packing and increased properties. And limestone is used because it gives you a better workability, it helps you fill the particles better. And so all our mixes that we have use limestone. So just to show you once more those materials, our idea was twofold. One, to take these combination of materials in whatever order we want them for, and then do a particle packing approach to find out what will cause optimal packing, and then use simple rheological tests and come up with rheological parameters that can explain the rheological behavior, and in some fashion connect particle packing and rheology, which will form the binder design, and of course check the reactivity using isothermal calorimetry and make sure that the combinations that we have selected are not detrimental in terms of early age properties. So that was our first part of designing the paste, which I'll go through. So we did about 33 mixes. Here are a few of those mixes and different combinations of fly ash and slag, combinations of metakaolin, microsilica, limestone of different sizes. Water binder ratio was between 0.2 to 0.24, depending on the application, depending on the binder, and depending on the flow that we wanted. But generally, just a set of mixes. And then we did particle packing, computational particle packing, assuming everything is circular particles, not the ideal situation, but there are a lot of work that has shown that considering them to be spherical particles and packing them in a three-dimensional volume will give you reasonably sufficient results to make decisions as to what set of particles to choose. So very complicated by doing the real shapes, we just do spherical shapes. And we define three different parameters from those packed microstructures. One is a coordination number, which is the average number of nearest neighbors in the microstructure. Number density, which is the number of particles in a unit volume, and mean centroidal distance, which is the average distance from the center of a particle to center of the microstructure. And all of these indicate packing of the microstructure, spacing between the particles as a function of the size and distribution of the particles. So the good thing is that you can actually start to get good indicators of different elements in your microstructure using these three quantities. So here is the mean centroidal distance, number density, coordination number, plotted as a function. So as number density increases, your centroidal distance comes down, obviously, as you expect. Your coordination number or number of neighbors go up. Simple relationship that you can come up with for all the mixes that we have evaluated in this work. So in terms of rheology, we started with simple rheological tests, parallel plate rheology, calculating yield stress and plastic viscosity. We have, after that, have done Wayne shear also, but these results are from, no, these are from Wayne shear results. These are Wayne shear results, actually, not parallel. These are Wayne shear results. So we did yield stress and plastic viscosity and also mini slump because we want to find some kind of an easy way to quantify what our spread is while we were doing the rheological measurements. So a binary paste, so one is with fly ash, one is with slag. So all these are fly ash mixes with F that you can see, and all of these are slag mixes with S. Binary paste with fly ashes were found to have relatively lower yield stress and plastic viscosity with respect to control paste. Interparticle frictional forces. Metakaolin shows higher yield stress, obviously, because it's much more stickier clay-like material. Fine limestone was found to improve overall packing, found to reduce interparticle friction in the mixes with quaternary binders, and lowers the yield stress and plastic viscosity, leading to increased flowability, something that we always found very beneficial with the use of limestone in a variety of different types of mixes. And right now we have Portland limestone cements that are coming out, so it's no more a rarity that you have limestone in your concretes anymore. So what are our selection criteria? So we have all these mixes, we have done all these particle packing, numerical particle packing experiments, we have done all this experimental rheology measurements. What is our selection criteria? So we do one criteria based on packing and one criteria based on rheology. The criteria based on packing is simply that the mean centroidal distance, the coordination number, and the number densities are either less than or greater than the corresponding values of the UHP control paste. So UHP control paste is a high-performance concrete designed with only cement and that too plenty of cement. And you know that particles cannot be packed as efficiently in this case, which means to get the same properties in a pure cement UHP as compared to something with multiple binding materials, you obviously had to have a much lower water binder ratio and in a higher use of admixture. So those are taken into account in how we did that. For the criteria based on rheology, just saying that the yield stress of my mixture has to be less than the yield stress of the control is not very efficient, because even 2 to 3 higher yield stress or plastic viscosity would not detrimentally influence the workability, especially when your packing is such high, right? So we came up with randomly, we took this number as 3, we did experiments to show that you actually can have a good workability in that case. So we used a factor of 3 for yield stress and plastic viscosity. For mini slump, several experiments, we want to use a parameter of 5, but we arrived at a 0.75 multiplier for that of control. Again, these are subjective qualifications that the user can change depending on how he or she wants to have the properties for their mix. So here is a selection criteria. This is from packing criteria. Out of all the mixes, there were 22 mixes that satisfied the packing criteria. That was not surprising because we did not do trial and error. Even those 33 mixes were selected very carefully. So it was not surprising that 22 satisfied those. 23 satisfied the rheological criteria that we wanted. We could have been a little more rigid with the rheological criteria, weaning out a few more. but we just, again, this was a methodology that we wanted to lay out that people can do based on how they find it efficient later on. And then once you have both packing and rheology combined together, we had 17 mixes that out of 32. So about 50% of our mixes satisfied the criteria that we wanted. Like I said, again, it's because we started off with a careful set of materials rather than doing a trial and error approach. So now we said, okay, can we do a combined rheology and packing coefficient? We came up with a simple packing coefficient based on the values of coordination number, number density, and centroidal distance, one which will go up and come down just to get you a value that can be reasonable in terms of a number. And then we develop a flow coefficient, which is square root of the mini slump area multiplied by yield stress and plastic stress. Higher value for gamma indicates better packing. Higher value for kappa indicates better workability. So we wanted, and then for these parameters, we took multipliers as 1 and 0.25. The packing has to be greater, which means better than the control, and the flow coefficient has to be greater than at least 25% of the UHP control. Like I said, the reason why UHP control was good because it had so much of admixtures to get to the flow that we wanted. So, but again, these multiplicative constants the users can change, and we have this entire process automated in the form of a software that can be used. We did oscillatory rheology, stress growth experiments to determine storage and bulk modulus and storage and loss modulus. You see that the plateau region for most space, which is roughly the storage modulus, generally limited to shear stress is less than 1 Pascal. Conventional OPC phase had those values to be 3 to 5 pascals, so significantly efficient way. Storage and loss modulus for all UHP phase are lower than 10 pascals, which is about 3 orders of magnitude lower than those of conventional OPC phase, without water reducer, of course. Number density, particle separation, all of those influences G and G prime. Limestone cement contacts and the consequent reduction in the particle forces. We have some zeta potential measurements, which I'm not showing now, but having shown that limestone cement contacts help reduce the oscillatory shear moduli. Okay, so now we have the paste all set. Now we will go to the aggregate design. And aggregate design also was based on a packing model. We had aggregates all the way from number 7, which is passing or retained on 4.75 mm sea level, so maximum nominal size of 4.75 mm. And all these different aggregates, 2 types of sand, a coarse sand and a fine sand, and we use steel fibers. We use polymer fibers also, but I'm talking about steel fibers in this work. So the way that we do packing is based on a compressible packing model, where you find the dry rotted unit weights of all of these components to find the maximum packing density of each fraction, and then use that in a compressible packing model, which again, we have made it into very easy to use software to find the optimum proportions based on maximum packing density. So we had a number of different combinations. We used 5 different aggregate classes, 3 aggregates and 2 sands, coarse and fine sands. And we use steel fibers also in this, 1/2 inch long steel fibers. So aggregates were all cleaned and washed and made sure that they don't have any dirt or deleterious particles. We used a compressible packing model. I'm not going to get to the details of the model. Basically, we define a compaction index and develop the packing factors for each class of aggregates, beta i's, and then based on the virtual packing density, which you can obtain from the packing density of each classes that you can obtain from your dry rotted densities, and some correction factors for loosening, wall effect, etc. You come up with a packing model, and we came up with hundreds of different combinations, theoretical combinations based on the experiments that we had, and each combination results in a unique packing value. These are all the packing values arranged in a descending order. So the one that has a maximum is up in the top. So this combination of aggregates that you see here, 0.4, 40% of number 4s, 10% number 8s, 10% of number 10s, and 40% of sand total gave us the highest packing density. So you can get, again, this can be changed once you have the individual dry rotted unit weights of the set of aggregates that you're going to use for UHPC. Now you combine paste and aggregates. Again, we had to do it through a sequential approach. So the aggregates were blended first with sand, and then we put in silica fume into that so that aggregate shearing will break whatever lumps of silica fume are available and make sure that silica fume is well dispersed. The other binder materials go in next. They are mixed with so all the other binding materials, silica fume, cement, all of them, they're mixed with some amount of water, typically a third of the mixing water. So you get like that. Then you add the remaining water in a couple of more steps. I just missed a couple of pictures in between. And then you add steel fibers, you mix for some more time, you get a very cohesive, a very smooth mix, which flows quite nicely. So this is the mixed design and large scale, reasonably large mixing of those mixes. Final properties, we got about 175 megapascal compressive strength for these mixes after 28 days. Some of them with higher amounts of fly ash gave close to 200 megapascal after 56 days or 90 days. Up to 20 megapascal flexural strength with 1 to 3% steel fiber reinforcement. And we see the stress strain curves for our mixes on the right here, usually. So just to conclude, talk about rational methodologies for selection of paste and aggregate phase using microstructural flow characteristics. One thing that I did not explicitly mention, but you would have seen in the mixture identifier that I've shown, all our UHPC mixtures had up to 30 to 50% of OPC replaced by other cement replacement materials, either by fly ash, metakaolin, and limestone, or silica fume and limestone, or combination of these materials. Better packing allows improved utilization of cement replacement and filler materials, while better rheology facilitates better dispersion of particles and improved mechanical properties, which is obvious. What this method does is, using simple rheological tests in the lab and simple particle packing tests, which uses only the particle size distribution of the mixes of the components of the mix that you're using, you are able to develop both of those indices and then combine them, and then do some initial tests to see what you would want, tweak the model or the multipliers based on what you want, and come up with a valid combination of the binder. Then go into the aggregate phase, again use a compressible packing model, come up with the packing of the aggregates, and make sure that you have enough paste that goes in to fill in the packing of the aggregates, fill in the voids between the aggregates. And that way we can develop and design a very functioning, very compact, and very efficient mixture without having to waste a lot of other materials. So high workability and high strength would be required. Now, if you wanted a UHP mixture for a precast application, which does not require a high degree of flowability, you can go back, use the same procedure for packing, but you can change your workability requirements in the paste design as we talked about earlier, and you can develop a mixture for that application also. So the idea is to generate a fluid methodology to design mixes for different types of application without having to do hundreds of trials. Of course, you need to do verification, validation experiments and trials to refine and confirm your values, but a good scientific principle that does not rely on out and out trial and error method. Thank you very much. This was a project that was funded by Arizona Department of Transportation. Thank you very much.
Well, thank you. Very good presentation. Particle packing is one of the biggest things when we design UHPC. So I very much enjoy the presentation, cover both the theoretical part and the rheology part, which is to justify this. We do have two questions in Coin A. I'll read that just so the audience can see that. The first one is very practical. You mentioned software available for both paste and aggregate packing. Where is this available? Is this available for everyone? I guess
So
I want to know too.
yeah, so right now we have it as an in-house thing that we used. We are still working on our final reports for our project, and then once we get a go ahead from our sponsor, we would release it.
You'll make that available for the public?
Yeah, we can. I mean, we have had enough Excel plugins for the software as of now that everybody can use it fairly easy.
That's great. Thank you. The other question is, do you have any mechanical property test
Oh, we have
results?
plenty of those. I mean, I can do another 3 presentations purely on mechanical property test. Yes, I just showed you the compressive strength alone. We have, like I said, we've got more than 175 to 200 megapascal compressive strength. We have about 50 to 20 megapascal flexural strength. We have work that has recently come out on stress crack width relationships. We have DIC studies on crack opening and fracture in these mixes. So yeah, we have lots of mechanical results at
Yeah, I would assume so as well. So I do have one question, since I don't see any other question. Yes, I don't see anything. Again, I'm glad to see the approach from both the theoretical parking as well as the rheology. So I'm assuming the theoretical parking, particle packing, is for the all the dry ingredients. Does that include the consideration of water?
No. So theoretical packing is only a selection criteria. So it is only dry. But we have modified it. We haven't used it for this purpose, but we have actually used the same thing in order to actually predict a reactivity when you have particles in a bed of water. So we have so basically a hydration model which uses water also with that. But in this case, we used particle packing purely as a binder selection methodology. So we did not do the hydration effects there. So it's not in water. It's dry.
But potentially you can use that in the future.
Yes, but we can.
Yeah, that's a lot of work to do. So yeah, once again, thank you for answering the question.